Hello, everybody. Thank you for coming out. Thank you for that introduction. So I'm going to be talking about packet capturing. Just a real quick survey. Can you raise your hand if you've ever done any packet capturing with Wireshark? OK, a lot of people. Perfect. Great, great. So, OK. Well, just in case anybody hasn't done it before, let's talk about what is packet capturing. Packet capturing is essentially when you are spying on the traffic that's going around on the network. There are some limitations to it depending on how you're doing it. If you're on a wired network, you typically only see traffic that goes to your computer if you're on a switched network. If you're using some older hardware like a hub, it sends all the traffic to everybody, so you can potentially see other people's traffic as well. With wireless, it's a little different because it's shooting it out into the air for everybody to see. So you can see other people's traffic if you have promiscuous mode turned on. Promiscuous mode is a special setting on your network device that says, yes, promiscuous mode is on. I want to see traffic that is not meant for me. And an important thing to note is that it doesn't block the traffic or man in the middle in that sense. You are passively watching it go by. Now, there are some caveats to that. For example, if you're on a public Wi-Fi network and you send out an HTTP request and somebody else sees it, they can potentially send you a response back before the remote server has a chance to respond through the gateway. And an example of that, I was at DEF CON last year, and a couple of these Russian guys sitting next to me wrote a program that basically listened for any HTTP request out there and immediately responded with a permanent redirect to a not safe for work site. So how can it be used? If you're coming from an application development perspective, it's good for testing your app, making sure your traffic is formed the way you want it to. It's really good for making sure things are encrypted. If you want to make sure things are logging in securely, really the only way to really verify that is to watch the traffic on the network. You can reverse engineer APIs. If you have like a mobile app that you can't really proxy through, you can just watch the traffic and see how it works, try and reverse engineer it. Seeing what traffic goes on in the background of your computer, this is an interesting exercise to do. Just run packet capturing on your computer and don't do anything and see what's going on. You'll be surprised how much traffic is going on in the background, whether it's Dropbox or ARPs or anything else, Windows services that you may not even realize are going on. You can steal credentials. It's good for network administration, make sure there's no rogue devices or malicious traffic. You can see if people are port scanning you and they shouldn't be. It's important for forensics and crime investigations. So if somebody attacks a large company and they keep packet captures, they can use that to actually identify what happened. And the last one is DEF CON Wall of Sheep. If you're not familiar with that, Wall of Sheep is essentially, at DEF CON, they set up this unauthenticated or unencrypted wireless access point for people to use that you're not really supposed to use. And the game is you go and you steal people's credentials off that wire and you put them up on a wall to shame them. So my motivations for doing this, I'm a hacker by nature. I like to know how things are going under the hood. I think it's Richard Feynman who has a quote that says, if I cannot create it, I do not understand it. So I think that really sums up a lot of hacker mentality. So I want to see how things work. Another reason is to make sure when I'm writing software and I'm writing login mechanisms that they are actually being encrypted the way I think they are. And I also mentioned make sure there's no malicious traffic, understanding how traffic goes on a wireless network. So for example, it's not always about being malicious, it's about understanding how safe your data is. So for years, Facebook did not use SSL. They only encrypted the login page. So they encrypted your password on your first attempt, but after that, your cookie got sent through the air in plain text. So you could sidejack people's sessions, and OkCupid, a bunch of other sites didn't do it for a long time. I found this really awesome Tumblr called HTTP Shaming. So you can go there and find a bunch of interesting sites that should be using HTTPS that are not. So some of the things we're going to talk about that you can do with the gopacket package in Go. You can get a list of network devices. You can capture packets. You can save packets to a file. You can read from a file. And this also works with Wireshark files and everything. It's all a standard live Pcap format. You can analyze the layers. You can even create your own custom layers with this. Haven't really had to do that, but if you had some proprietary protocol that was going over the network and you needed to create a special decoder for that, you can do that. Cover Berkeley packet filter, so you can filter your traffic and not get everything, and also injecting packets and following streams. So most of you raise your hands, and I'm guessing you probably use Wireshark. Wireshark is the most popular GUI interface for capturing packets, and there's the command line version called tshark. TCP dump is the command line tool for dumping packets either out to your screen or to a file typically. DriftNet is an interesting program. It comes with Kali Linux, and what it does is it only looks for images going on the network. So it puts up a black screen on your screen, and then it just starts showing all the images that are going by that people are looking at. There was a plugin called Firesheep, which was a Firefox plugin that was essentially used to sidejack people's accounts and steal cookies like I was describing earlier. So as far as prerequisites, in order to do all this, you're going to need Go, and you're going to need libpcap or WinPcap. libpcap is a C library. It's part of the TCP dump project, and I have a link on my website, devdungeon.com, about using the C library, the C version. WinPcap is pretty much a completely compatible version of libpcap, but for Windows. If you're writing it in C, you essentially just have to change out your headers, and you're good to go. With the Go programs, though, you don't have to change anything. You can take your same Go program, compile it in Linux, Mac, Windows, without changing anything. So gopacket is the actual Go package that I'm talking about. It utilizes libpcap, but it also supports PF, ring, and AF packet, although I've never needed to use those. That's the link to their GitHub, and I also have a tutorial on my site that goes into depth about using the gopacket package. And if you can see from the image here, it's got 31 issues, 650 stars, 60 watchers, 127 forks, so it gives you some idea about how much it's used and how popular it is. There's a couple sub-packages. There's the root package, there's the Pcap package. The Pcap package is essentially just a pure wrapper around the C library. The other layers, the next package, layers, that is probably the most powerful one that you're going to be using for actually decoding and interpreting the data. Pcap Go is another one. It's really small, and the only time I've ever had to use that is for actually writing out the files. So some of the notable types that are in this package, just to give you an idea, there's a decoder type for decoding different layers. There's flows, layers, packet source, and payloads, which is the actual data at the end. So this is our first code example we're going to look at. There's one import, and it's just the Pcap subpackage, which means we're only using functions that come straight from the C library. And in this case, we're just going to call pcap.version, and we're going to get a string back that describes the version. That's more like the hello world, just to let you know your libraries are hooked up and everything's working well. So the next thing you want to do is find a network device that you can actually use to start capturing packets. So you create a slice of Pcap interfaces, and then you call find all devs. Now, devices and interfaces, the word can be used interchangeably, and they do. So what is a Pcap interface? A Pcap interface is just a name and a description. The name is actually what's important. That's what we're going to be using to identify the device. On Mac, it's typically EN0, on Linux, F0, WLAN0, and on Windows, it's curly braces, dashes, letters, and numbers that you will not pronounce with your mouth. And then it contains your addresses. This is your actual IP addresses of your network interfaces. And so if we look at that, it's got an IP address and a net mask. And those use the core net package from Go. So nothing too magical there. So now that we know how to find devices using find all devs, we can then open a device. We use open live to open a live device. And you see we pass it a couple parameters here. We pass it the name. In this case, F0 would be a Linux device. The snapshot length, which is how much you're actually going to capture of the packet. 65535 is typically good for all cases. If you're not interested in the whole thing and you really only want just the header information, you can trim it down smaller, maybe 1024, something like that. You don't have to capture everything. Promiscuous mode, true or false, and the duration of the timeout. Now this one's interesting because if you put something like a 30-second timeout, it won't flush the packets until every 30 seconds. So what'll happen is you'll say, get all the packets and print them out to the screen. You won't see anything for 30 seconds, and then you'll see all the last 30 seconds worth of stuff dump out at once. So they introduced a negative timeout, where if you give it a negative timeout, it'll just flush everything immediately. And it's a handle, so we just defer the closing of it. So alternatively, instead of opening a live device, you can open a file. You can open an offline file. Now, you can use any Wireshark file or anything like that, or a TCP dump file. They're all standard format. And in this case, you pretty much do the exact same thing. You're going to call open offline instead of open live. But what you get back is a handle that it's going to get treated the same way after you do that. So once you have a handle, whether it's from a file or a device, you create a packet source out of it. And you essentially just pass it the handle, and then you call a function called link type. So you don't even really have to know what the link type is. It'll figure it out for you. But typically, it's an Ethernet. It's an Ethernet thing. So once we have a packet source, the most obvious thing to do is read a packet from it. So they provide this function called next packet. And what you get back is a packet. And there is a stringer function on it, so you can just print line. It'll print out some interesting information. It'll print out timestamp, how long the size of the packet, the different layers on it and everything. I'm going to do some demos later, so you'll actually get to see some of this output. So if you want to read all the packets, you don't just keep calling next packet over and over. They actually have a function called packets. And you can use range to go through the packets. So you say for packet in range of packets. And then you can process the packets in any way you want. In this case, I'm just printing them out, but I'll show you what you can do with them later. So sometimes you want to capture everything, but other times you just want to capture specific things. So you can use Berkeley packet filters. They created this human-readable, more or less, way of creating filters. So in this case, TCP and port 80. So it's going to limit anything it returns to being basically HTTP traffic. Hopefully, that's what's going over 80. If you're doing it in C, you have to create the filter, you have to compile it, and you have to attach it. In Go, you just call set BPF filter, and you're good to go. You want to do this after you create your handle, but before you create the packet source and start reading packets. So a couple examples of other filters in case you haven't seen it. If you just put in an IP address, it's going to say anything to or from that IP address. The next one, 128.3/16, you're saying anything that's on that subnet at all, starting with 128.3. You can say port 53, which is going to hopefully find DNS traffic, either to or from. The next one, it shows how you can and or things together. You can say host 888 and UDP port 53, which should be Google DNS traffic. And then you can say, so this next one's another net mask where you're saying anything on the subnet of /22 and port 80. And then the last one says HTTP or HTTPS traffic that's not host.1, which is typically your local host. So you're saying any traffic that's not mine going on the web. So if you want to store this information, you can write it to a file. So you use the built-in OS create to create a normal file handle. And then you wrap it with the Pcap writer. So then you say pcap go.new writer wrapping around the file that you created. Then before you start writing packets to it, you first initially have to output a header, some header information. And they have a function for you called write file header. You just pass it your snapshot length and your link type. And then you're ready to start writing packets to it. So in this case, if you look at the outer loop, we're just ranging through all the packets on the source like we saw previously. And in this inner block, we're calling write packet. So for every packet we find, we are writing the metadata and the data. Now, this is good if you're capturing on a live device, so you can capture things for later looking at. But if you open a file and do it this way, it's just a really fancy way of copying a Pcap file. So now that you have a packet, what can you do with it? Packets are built in layers. Most common layers we see are Ethernet, followed by IP, followed by TCP. And you can query a packet. You can say, for each, OK, in this case, we're doing a range on packet.layers. When you call .layers on your packet, it's going to return you a slice of all the different layers that it recognizes in that packet. Now, they may be ARP layers, IP, there's all kinds of different things. I'm talking more about those later. And then we're just printing out from print line the layer type here. So this will just say Ethernet, IP, TCP, very simply. So let's talk a little bit more about the packet layers in case you're not familiar with them. Think of them like this. They are nested, and they're almost recursive if you want to think of them that way. So essentially, every layer starts with, it's got some kind of header, followed by the rest of the data. Now, the way it's built into layers, you've got your header, and then the data is actually another layer that has its own header and more data, and that data there is another layer with more headers and everything. So if we look at the most common layers, I understand this is maybe a little difficult to read, but the important thing to look at here is that Ethernet headers are very simple. You've got a source MAC address and a destination MAC address, and that's about it. And then you've got your data, which is going to be typically IP. So if we're looking here at the IP packet, you'll see it's a bit more complicated. There's a lot of different things here. It's got version, it's got header length, total length, flags, time to live. You don't need to know all these. It's just important to understand that with the IP layer, it's got the source IP address and the destination IP address. Those are the really important things. Then let's go up one more layer to the TCP layer. Now this has the port numbers, the source port and the destination port, as well as a bunch of other things like SYN flags and ACK flags. So again, you don't need to know all these details. You just need to know how the headers are nested and that they each have their own unique headers with sets of information. So let's say we have a packet and we want to look at the IP layer. So what we do is we say packet.layer, and then we pass it the layer that we're interested in. We're interested in layer type IPv4. And then it's going to return something. It might return nil, which means it didn't recognize an IPv4 layer. It may not be an IP packet at all. So you just check whether it came back nil, and if it doesn't come back nil, then you can go one step further, and then on that IP layer, you do some Go stuff, and then you actually can access the information that you see in the headers. And I'll show some more details there. So same thing for the TCP layer. You call packet.layer, and you tell it what layer you're interested in this case, layer type TCP. Check if it's null, do some dereferencing, and then you've got your source port and your dest port and all those other things that are available to you in the header in that struct for a TCP layer. So decoding packet layers. Because all the layers are nested, the layers, when you decode one layer, it returns the next layer in line. So if you're interested in starting at the Ethernet layer and seeing everything above it, you can decode it with this first line here. So we say gopacket.newPacket. This is actually creating a new memory struct. So new packet, and we pass it in the original packet we got, which is kind of an unintelligent packet. It's kind of raw data, more or less, and we haven't quite decoded it yet. So we give it the original packet data, and then we're saying layer type Ethernet. We're telling it what layer we're interested in. And the last parameter there is the decoder method. Now, the default is actually going to create a new memory object and copy everything over there. So if we look at the next example, we see IP packet. So if we decode it starting at the IP layer, that means we're ignoring the Ethernet layer. We're not interested in anything below the IP layer. We're only interested in IP layer and up, which is what we're going to get back. Now, in this example, I used IPv6. And the last parameter is no copy this time instead of default. So instead, this one, if you tell it no copy, it will not create a new memory struct. It will end up pointing back to the original thing you had. So as long as you don't manipulate it and change it, that one is safe to use. The last one is exactly the same, except we're looking at the TCP layer up and only. The important thing here is the last parameter, gopacket.lazy, means it's going to lazily decode things, basically only when you need them. The important thing there is that it is not thread safe. It is not Go routine safe. So don't send them through channels and through routines. So there is a faster way to decode. Instead of creating new memory structs every time, you can create them once, and it will reuse those structs for every packet it has. Now, the pros and the cons here is it's going to be faster. It's not going to use up a lot of allocating and things like that. The drawback is it's only going to recognize the layers that you predefined here. In this case, I'm defining an Ethernet layer, an IPv4, and a TCP layer. So if it gets a packet that doesn't fit in those layers, it's not going to decode it, and I'm not going to get it back. You can pass it multiple things. So you can create an IPv4 and an IPv6, and it will intelligently say, OK, there's no 4, but there is a 6, and it'll fill those out for you. So you can have more than just one stack. So we create everything we need here. We've got our variables for the layers, and then we create a parser. And we tell the parser what layers we're providing it. You can add as many layers as you want at the end there. And then we're creating a special slice called decoded layers. It's empty. It's just a slice of layer types that we're going to populate in the next slide. So again, on the outer loop, we're just ranging through our packets. And on the inside, we're actually going to decode them. So we call parser.decodeLayers. We give it the packet. And then we give it our slice of decoded layers, which is we're going to populate. And then we can range through that decoded layers and see everything that it found. And we can see whether it found one of them or all three of them. It does support a number of other layers besides Ethernet, IP, and TCP, things like ARP, Cisco Discovery, DHCP, DNS, pings, USB. There's 118 layers registered. It's got a lot of support. And you can make your own if you need to. So there is also some common packet layers that it provides you pointers directly to them. So every packet has these functions on it. They roughly translate to some of the OSI levels, but I'm not going to get into that. So link layer, if you call that, you're typically going to get something like Ethernet. Network layer, IP, transport layer, TCP, and UDP. An application layer is essentially your payload that's going to your application at the end of the day. It may be some JSON. It may be an HTTP formatted request. And there's an error layer that lets you know if anything went wrong. OK, so let's talk about custom layers. This is more of one of the involved examples, but I broke it up so I think you guys can digest it. So first, you have to register your custom layer. And what you do there is you give it a unique ID and a unique name, and then you pass it a function that knows how to decode it. We haven't created this function yet, but the function is called decodemyLayer. So on the next slide, we have the struct that is actually going to represent our layer. So once we do decode it, we have a struct to actually interact with. In this case, it's very simple, a header and a payload. So then we define our decode function. So we have a func called decodemyLayer. We pass it in the raw slice of bytes. And then what it actually does, so it's calling p.addLayer, and then it's adding our layer. So when you call packet.layers, and it returns the list of layers that it found, this is how you're adding your layer to it. So when you call .layers, it knows my layer is in there. So in this case, we are adding my layer, and we're creating the struct. We're basically splitting up the data. We're taking the first 4 bytes, calling that the header, the rest of the bytes, and calling that the payload. And then we return the next layer in line. In this case, our layer would be below the Ethernet layer because the next thing we are returning is the Ethernet layer. It's kind of a contrived example, but OK. So there's a couple functions we have to satisfy so that when we call our layer, if we call some functions on the layer, it knows how to handle it. So layer type, layer contents, and layer payload. Layer type actually just returns, it tells it what type it is, so we can reflect on that. Layer contents is the header, and layer payload is the payload. And we define that when, going back, you see where we said data up to 4, data after 4. That is creating the header and the payload that we're going to be returning here. Then once we have all that defined, we can decode it the same way we did any of the other layers. So in some of the examples you saw before, we were saying new packet with layer type Ethernet or layer type TCP. In this case, we're saying my layer type. And what we get back is the decoded packet, where we can say decoded packet.layers, and it'll tell us that our layer is on there now. You're not going to really use that unless you're dealing with some proprietary formats, but I wanted to go over it anyway because it is a very powerful feature. And they created 118 layers, so there might be cases for more that you need. So creating packets is different than creating the layers. Packet is actually the raw slice of bytes that we're going to be sending over the wire. And I mentioned that they're all nested and serialized. So what we're doing here is we're creating a new serialized buffer, which is a special type that is just slices of bytes, essentially. We create an options. Those things are required. Then we call serialized layers. And we serialize all the layers into the buffer. We're passing it the buffer. That's the one we're going to fill up. And the options, which you don't really need to fill out. In this case, I'm creating an empty Ethernet layer, an empty IP layer, and an empty TCP. There's no ports. There's no MAC addresses or anything. It's basically a null packet with ABC as the payload. But when you're done, you can just call write packet data to your handle. And what you do is you don't write the buffer struct itself. You call buffer.bytes, which actually returns the raw slice of bytes that you're just going to shoot off the wire. And it's as simple as that, write packet data. So that's how you inject packets or send packets out. Another thing that you can do, which is really powerful here, is flow and endpoint. So this essentially lets you say, I only want traffic that's going from here to there, this stream between these people or these ports or whatever. So in this case, when you create a flow, the flow is just the definition. In this case, the definition is source of UDP port 1000 and destination of UDP port 500. So anything that's going from 1000 to 500 is going to be considered in our flow. So then what you do is, you're going to have to do this for every packet, essentially. So given a packet, you check the network layer. And then you take the network layer, and you check the transport flow. And you see if that flow matches the flow that you defined. And if it does, then you have found something that goes inside that stream. It does not give you a big slice of all the packets in that stream. You have to check each one yourself and see if it fits in your flow. So some of the things you can do with this, you can see if there's any blacklisted IPs trying to hit your network. It's good for fuzzing network services to see if you can break things, find some security flaws, maybe some buffer overflows. It's good for monitoring your network traffic flow, maybe just to see how much traffic is going around. Maybe you want to see where things are going and where things are coming from. Port scanning. This is interesting. If you want to send out null scans, or they call them Xmas packet scans, where you basically turn everything on. A null scan is when you set everything off, all the SYN flags, all the ACK flags, everything off, and you send out a null packet and see how things respond. That can be useful for if there's stateful firewalls or stateless firewalls, they handle SYN and ACK packets differently. If you send an ACK with no SYN, a stateful firewall will understand that there was no connection there, and a stateless one will not, and so they behave differently. You could potentially implement a firewall with this, but again, it doesn't actually, and the IDS too, because it's not actually blocking the traffic, you have to basically recreate and send out the packets again if you want to act as a blocker in the middle, where you're saying, I get the traffic, and I'm going to decide if I want it to go on. You have to you basically copy that packet and say, okay, yes, I'm send it back out. It's okay. So, okay, I'm just going to go straight into some of these demos real quick. We can do some questions at the end. Okay, is this readable? Guys in the back, hands if you can't see. Okay. So I'm going to roughly go through the examples that we went through in the slide. So this one is just catching the version. And if we run that, it just prints out the string. In this case, it's live Pcap on my Apple MacBook Pro. So the next example is going to be actually finding devices. So in the slides, all I covered was find all devs and then print it out. But in this case, I've got some block of code here that's actually going to print out the name, the description, and all the IP addresses and everything. So if we run this, we'll see that there are a number of devices on this machine. The one at the bottom there is the low. That's your loop back. And if you go up to the top, you'll see my main one, which is my EN0, and you'll see it's got an IP6 and an IPv4 address. So this is for capturing a single packet. The imports, all we need here is gopacket and Pcap. These are all the variables we need to open the device. We need the name, the snapshot length, promiscuous mode, timeout. We need a handle and an error. So we're opening device using openLive, passing in everything we need, deferring the close. We're creating the new packet source from our handle that we opened. And then we're calling next packet just to read one packet and print it out. So let's see what the first packet it finds is. Okay, if we see packet 233 bytes, timestamp, layer 1, Ethernet. And we actually see, if we scroll along, source, dest Mac. And you see the desmac FFFF, that means it's a broadcast. It wasn't really intended for me, it was going out to everybody. One thing I want to mention about broadcast traffic. Some protocols try and log in with broadcasts. There's a program called Responder. Now, it basically listens on your network, and it listens for these broadcast protocols. So one of these protocols says, hey, I'm here. Is there any one of these type of servers that I can log into? Responder will go, yes, me, send me your credentials. And so it's kind of an insecure way of logging things in, but some companies do it that way. Some of the other layers we see, it's got an IPv4, and this one is a UDP packet. And the payload comes out to 191 bytes. Now, this is just the standard stringer function, so this is how it prints out everything if you just call print line on the packet here. So the next one is going to capture more than one packet. Okay, so everything up to here is the same. We're just opening the device, creating the packet source, and then we're going to iterate through the range of packets. In this case, I'm not just going to print out the packet. I'm going to do a little more inspection. So we saw earlier, you can call packet.layers and get a list of all the layers on that packet. So first thing we're going to do is print out all the layers that it finds on the packet. And then we're going to look for a couple of specific layers. We're going to look and see if it has an IPv4 layer. If it does, we're going to print out the IP addresses. And then we're going to go down to the TCP layer. And if it finds a TCP layer, we're going to print out some of the flags and some of the port numbers. So let's go ahead and run this. Just see what it finds. Okay, I'm going to stop it. Let's look at some of them. Okay, find most of them decoded properly. Every once in a while, you will see packet layers, Ethernet, IPv4 error. So, and it'll say it had trouble decoding it. Maybe it was something it didn't recognize. Maybe it was malformed. So as you can see here, when you print out the packet layers, it's the very human-readable format. So we see very clearly what layers are here and whether it detected an IP layer and whether or not it detected a TCP layer. So this is how you can do some of the analysis on packets. And so it does here, you can see source port. It does intelligently add the protocol if it's a common port. So the next example is capturing with the filters. And I'm using the example that we saw on the slides where it just says TCP and port 80. And I'm just going to use the stringer to print it out. So go ahead and run that one. I'll do a quick curl on a non-HTTPS site. That way we can make sure we get port 80. And you'll see there's a whole bunch of packets because it can't fit everything into a single packet. When you're doing a TCP connection, it's actually going to send you back a whole bunch of different packets. And there is a line in here, or a variable called sequence. So sequence is how your network, your computer knows how to reassemble all the packets when it gets them, because they're not necessarily going to arrive in the correct order. So writing a file, we saw, okay, we have to create the file using the built-in Go file create. We write the file header. Then we're going to open our live device. We're going to create a packet source so we can start reading packets from our live device. And then as we go through all of our packets, we're going to print it out, and then we're also going to write it to a file. And in this case, I'm counting the packets, and I'm going to stop as soon as I reach 100 packets. Let me stop my other one. So it should find plenty of traffic. I'm not even doing anything. This is all just background traffic. It's going to find 100 pretty quick, but let's speed it up with another curl. Okay. I just went ahead and stopped it. So the next one is actually how to open and read it. Now, instead of calling open live, we're calling open offline, and we give it the file name. In this case, I just wrote a test.pcap. So we're just going to call open offline, and then we're going to process the packets exactly the same way, because after you create a handle, it doesn't care whether it's a file or a device. So we create a packet source from our handle, and then we're just going to iterate through them. So this is good for analyzing things after the fact. Let's say you ran a Wireshark and you found a bunch of really bad things. Now you need to hand it off to your incident response team or your forensics investigator, and they need to start going through. So they can go through and look at everything and see where the source of the problem was. And you can apply your filters to this too. So you can run through it once, look for everything on port 80, change the filter, start looking for other things. That's the nice thing about having a file. The last example I want to cover here is actually sending packets over the wire. So open live, nothing new there. We're going to create the layers. In the example in the slides, it just created a bunch of empty layers. In this case, we're actually going to fill out some of the information. So you'll see here, first we create the Ethernet layer. We're going to give it a source MAC and a dest MAC. Those are totally made up, so it's not really going to go anywhere. The IP layer, we give it the source IP, dest IP, version, header length, things like that. TCP layer, all we need to give it is the ports, really. You can tell it whether you want the SYN or ACK flag on. Now, if we were doing some port scanning, again, if you wanted to turn all the flags off, turn all the flags on, you can do that. And then we give it a payload, which is just a slice of bytes in this case, something arbitrary. So then when you have all your layers, you need to serialize them using the serialize buffer. And you call serialize layers, and the buffer, which is what we're going to fill up, and then all the layers that we want to stack up. And then finally, we get the raw slice of bytes calling .bytes, and then we just say write packet data and give it the slice of bytes. Now, you don't even have to go through all the work of creating these layers. You could just create a raw bunch of bytes and send it out over the wire and hope for the best. But if you want it to actually work and you want network devices to recognize it, you want to fill all these things out correctly. So this is going to be kind of anticlimactic, but it's sent. So those are all the examples I had. I guess the only other thing I want to mention is this editor I'm using here. It's called Lite, IDE. I'm sure some of you want to throw tomatoes at me and tell me I should be using Vim, but I've been really happy with this editor. I really like it, and it's got some nice features. So I do recommend you give it a shot if you're looking for something to try out. So I do have about 10 minutes for questions. Does anybody have questions?